We are halfway through our lecture on the sun. I will finish that today. Just things to note. There is a quiz this week, so make sure you do the quiz on D2L. I gave you a week off last week. There is not homework. There's homework this week, but there will not be homework during spring break. But be sure to always check up on the Mastering Astronomy website, right? All of the homeworks are listed there in the calendar. Are there any questions? All right, so what we were last talking about is that the sun, there's actually a lot of activity on the sun, and it's related to its magnetic field. So some of what we're talking about are sunspots, these slightly darker regions on the surface of the sun that are regions where magnetic field lines are emerging or connecting to. There's also solar flares, just the bright regions on the sun that suddenly appear. There are solar prominences where you see this kind of filament or arc of material that, as we'll learn, actually are plasma following the magnetic field lines, often connecting sunspots. And then you can even have one of those filaments actually break apart, forming what we call a coronal mass ejection. We'll see some videos of this stuff today. So here's a nice up-close view of sunspots where you see, as I emphasized last time, they're not literally black. This is only when you view them through filters that lessen the brightness of the sun so you can see anything at all. They're still very hot, but they're about 1,000 degrees cooler than the rest of the sun's surface. And you can see this kind of furriness is, you're actually kind of seeing the magnetic field lines the same way if you ever put iron powder on top of a magnet, it kind of looks furry. That's the same sort of effect we're seeing here on the surface of the sun. And last time I talked about how we actually can map the magnetic field on the surface of the sun using spectral lines because of this cool effect called the Zeeman effect, which is that when we look at a spectral line, it actually splits in the presence of a magnetic field. And the degree of how far that one line turns into two lines tells us how strong the magnetic field is when we look at the surface of the sun. And so what we learned, for example, is that sunspots tend to have magnetic field lines going from one spot to the other. Like one is acting like a north pole, the other like a south pole. And this actually explains why a sunspot is a little bit cooler than the rest of the area, is because these magnetic field lines trap charged particles. And remember, the sun is a plasma. So it's made of these plus and minus charged particles. And if they can't move because they have to be corralled by these field lines, they can't exchange energy with the rest of the sun, so they cool off. And so one of the really neat dynamical features of the sun, related to sunspots among other things, is that the sun appears to have a cycle that lasts about 11 years. Every 11 years, the sun goes through a cycle where it gets, well, here I have 4 things shown on this plot, just showing 3 example cycles. So we say there's a region of solar minimum here where the sun is slightly less bright. It's only 1% or so. It's not enough to change the weather. Slightly less bright, fewer sunspots, fewer flares, less general activity on the sun, okay? And over the course of 11 years, it moves, it goes up, well, halfway so about half of 11 years, about 5 or 6 years, it goes to solar maximum, where there's lots of sunspots, lots of flares, lots of solar activity, and the sun overall is slightly brighter. Okay, and then it goes down and up again and down and up again every 11 years. And so here's a couple pictures. So here's a maximum that occurred around the year 2000, where you see lots of sunspots. And then, about a decade later, you take a picture and it's solar minimum. There's hardly any sunspots. And the exact same thing, you can take pictures of the number of flares and prominences and all of these arcs and activity are high when there's lots of sunspots, solar maximum, again, the year 2000. And again, a decade later, you see much less activity at solar minimum. And it's this sort of thing, in particular sunspots, because it's one of the clearest ways to see something that's changing on the surface of the sun. People, since Galileo, could see sunspots by just using a filter, something to make it everything on the sun darker, or you can actually do it using a pinhole to cast a shadow of the sun on like a piece of paper. You can actually see the sunspots. So Galileo was the first to do this. And for a few hundred years, people have been doing continuous daily observations saying, oh, there's 10 sunspots today, 8 sunspots 2 days ago, and just recording it. And you get graphs like this. So here's since a little before 1970. You see that this cycle has been going on for a long time. So here's the cycle since 1970. And we have kind of a convention. So we call this the International Sunspot. So you see it solar maximum. There's often 100, 200, sometimes up to 300 sunspots. On average, it's about 200 sunspots. And then in solar minimum, there's only 10 or 20 or something sunspots. In fact, since people have been making these recordings for hundreds of years, we can actually go back to the 1700s and see that the sun has been doing this pattern over and over again for hundreds of years. So it's a very steady 11-year cycle that the sun has been doing for a very long time. And in fact, even going back a few hundred years, people have not only recorded how many sunspots there are, but they've recorded where they are on the surface of the sun. So on the bottom here, you just see the number of sunspots going back to 1870, and you see that cycle of fewer and then more, fewer and more sunspots. But then up here is showing where they are. So up at the top is the North Pole of the sun. Here is the South Pole of the sun. And people see that at minimum, solar minimum, there's very few sunspots. They start up at mid-latitudes, like 30 degrees north or 30 degrees south. And then as you watch them over that 11-year cycle, the sunspots move more towards the equator. This is called the butterfly diagram. You see that the sunspots are moving every 11-year cycle towards the equator. And then the cycle starts over again, where the sunspots are up to the top, and move and so on. And part of what's going on is that the sun rotates at different rates. The equator rotates faster than at the North Pole. Okay, it takes about 38 days for the stuff on the surface of the sun to rotate at the North and South poles, but only about 25 days for the surface to rotate at the equator. And so, if you were to follow a bunch of points on the surface of the sun over a few days, they would travel like this. They would start. They would not move much near the poles, and they'd be moving much further along the equator. Here's a neat diagram showing, actually, if you go out from the center of the sun, near the center of the sun, everything's rotating together. But as you get towards the surface, it starts to change, and the equator is moving faster. And what this means, so all of this is related, this 11-year cycle, all of this is related to a magnetic field of the sun as a whole. So if you think of the sun, just like the Earth has a magnetic field, has a North and South Pole due to the rotation of the core of the Earth, well, the sun has the same thing. It's rotating, and it has a North and South Pole. And you can imagine those magnetic field lines going up from the South Pole up through the North Pole. But as the sun rotates, that causes those magnetic field lines to get distorted in this way. Okay? And so you have the sunspots kind of following the magnetic field lines, moving more towards the equator. But then it gets so distorted near the end of that 11-year cycle, it actually totally breaks, and the magnetic field reverses on the sun. So I've actually mentioned that every few thousand years, the Earth's magnetic field also reverses. The sun's magnetic field reverses every 11 years, and that begins a new cycle. Okay, so this cycle we see slightly lower, slightly less bright, slightly more bright, fewer sunspots, more sunspots, fewer, more solar flares. It's all related to the changing, the 11-year cycle in which the sun's magnetic field flips. Okay, and as it's about to flip, it gets more and more twisted. There's more sunspots. There's more flares until it flips, and then it's calm again, and it keeps rotating in the process. Here's a picture of a filament with Earth to scale. So you can imagine that there are magnetic field lines kind of connecting a sunspot here and a sunspot here. And along this filament is a huge amount of trapped plasma. You see just how large this is on the surface of the sun compared to the Earth to scale. Here's another. So these are called filaments or solar prominences, another example. Here's another one with the accompanying solar flare, meaning just a brightening, tremendous amount of energy being released from the sun's surface. And here's something even more dramatic. You have a flare, and then the development of a prominence, or this filament or arc, you could call it. And then over in the last frame, that arc, which was billowing out, actually breaks apart. And therefore it releases, kind of burps out a tremendous amount of charged particles into the solar wind. I'll show you a video of this in a bit. Okay, so one thing that I just want to mention before asking your poll question is that all of this, I've mentioned that the sun, has sunspots come and go, solar flares come and go, just general activity changes on the sun's surface over this 11-year cycle. The position of those sunspots changes. One thing I do want to emphasize is this has nothing to do with the actual fusion that's happening in the center of the sun. The sun is producing the same amount of energy in its core. This cycle has everything to do with the magnetic field of the sun and nothing to do with the energy production inside the sun. So putting all of this together, which of the following statements about the sunspot cycle is not true? And I'll ask you this as a poll question. Remember, which is not true. Okay, 5 more seconds. Okay, and most people got the correct answer. So all of these are true, except one thing that's not true is that the fusion in the center of the sun, the rate of nuclear fusion, the energy production inside the sun does not change. Okay, so that's C is the correct answer here. But the magnetic polarity of the sun changes, the number of sunspots changes. They do start at mid-latitudes and then move towards the equator. And the number of flares also peaks every 11 years. Right, here's another question that I'll just answer for you, right? Which of the following processes is involved in the sunspot cycle? Well, the only thing here that is involved is the winding of magnetic field lines due to the sun's rotation. We just talked about that. There is a tiny amount of change in the visible light, but definitely not a large change. So tiny change in the visible light, but not a lot. Here I'll show you some movies showing solar activity, examples of solar activity. So one thing that we have is the Solar Dynamics Observatory, or SDO. That's a dedicated satellite just to look at the sun. So here's an example. Oops. So here, all of 2015, where 1 second corresponds to 2 hours on the sun. We won't watch this whole thing, but so there you go. So here you're seeing, of course, the sun rotates, but you're also seeing all sorts of solar prominences, and you can actually see that the plasma are following, kind of these arcs of plasma are like following, like you think, little magnetic field lines between little north and south poles all over the surface of the sun. It's very, very active. A beautiful, active, dynamic sun. So you can watch the rest on your own time. Let's see what else. There's a large flare where 1 second corresponds to 30 minutes. Yeah, so this is pretty cool. So here you see a flare where it's sudden brightening, and then a coronal mass ejection. Isn't that amazing? You see, like, the sun just releasing a tremendous amount of stuff out. Some of it moves totally outward into the solar wind. Some of it falls back under gravity. It's called a coronal mass ejection. And you see briefly, there's the filament that forms the coronal mass ejection. So see right there, we'll go back slightly. See there's a filament connecting here to here along magnetic field lines, but then it bows outward until it kind of explodes. And here's another one. This one, 1 second corresponds to 6 minutes. Another flare and filament. Here's a filament forming. So you see this hot plasma raining down along those magnetic field lines. So if you're getting the sense, the sun is actually a pretty active place. Lots of stuff going on the sun's surface here. It's a large filament. Let's click on this link.
is releasing a coronal mass ejection, and you see the surface is kind of forming this canyon with north-south field lines of plasma connecting. There's another view of the same thing. A little scary, right? I mean, this is our sun. It looks like it's exploding, but of course, this happens all the time. Okay, I also want to show you some simulations of the magnetic field lines themselves, so you can kind of see the correspondence between that and the plasma that follows the magnetic field lines. There's a simulation showing, so mostly a North Pole, say on top, and a South Pole on the bottom, but then you see all these field lines connecting North to South poles on what are sunspots. There's a lot of magnetic activity on the surface of the sun that is related to most of the solar activity. There's going to be a simulation showing the field lines of a coronal mass ejection. And you see it starts out as these filaments connecting like a north and south pole on the surface of the sun where there will be sunspots, but then it kind of bows outward until it just totally releases out into the solar wind, and that's a coronal mass ejection. Any questions so far? So the next thing we want to understand is what powers the sun. How does the sun get so much energy? And that's through nuclear fusion. Now, I need to go over a little bit of about the forces in nature to describe the force involved in the sun. So you're familiar with the electromagnetic interaction. Governs electricity and magnetism. It says that there's a force between plus or minus charges. And that's actually what involves most of the biological chemistry, bonds and cells and DNA and all that. Another force is called the weak interaction. That's involved in radioactive decay, and involved in the production of neutrinos. That is a particle we'll talk about. And then most important for fusion in the sun is called the strong interaction. This is what binds nuclei together, right? Atoms are defined primarily by their nucleus, right? It has some number of protons and neutrons. What binds those together is the strong force. And it has to be strong because they don't want to go together. There's protons want to repel due to the electromagnetic force. And then not only does it bind the nucleus together, it also binds protons and neutrons themselves together out of more fundamental particles we call quarks. Okay, finally, and you're also, of course, aware of the fourth force in nature is gravity, which is important in astronomy. Right? We're talking a lot about gravity. In the case of the sun, if it weren't for gravity, the sun would just explode, right? But luckily, there's gravity holding the sun together. Okay, so we're going to be talking about the nucleus involved in producing energy in the sun. So what is a nucleus made out of? It's made out of protons and neutrons. Protons have a charge, okay? Proton has the symbol P. Neutron has about the same mass as a proton, but it has no charge. That's why it's called a neutron. Neutron for neutral, meaning no charge. So protons and neutrons together in a nucleus, where the protons determine the atomic number. They determine what element on the periodic table it is. It's the charged particle. Neutron just adds mass. And one thing to keep in mind, right? The strong force has to be strong, because if you bring protons together into a nucleus, the electromagnetic force makes them want to repel. Like charges repel. It's only the strong force that can bind them together into a nucleus. Okay. So the only force that can overcome that electromagnetic repulsion is the strong force. That's why it has to be strong. That's how you can remember the name. Now, this is a very famous curve in physics. A single curve tells us a tremendous amount of information. It's called the curve of binding energy. And what you have are all the elements in the periodic table from left to right. And what this shows is how much energy it would take to basically break apart this nucleus per nucleon. So what you see is it's hardest to break apart iron and nickel. They're at the very top of this curve. And for that reason, they're the most stable. And one way that maybe will help you understand the meaning of this curve better is to basically flip it upside down. In which case, the same curve is describing what I'll call the mass excess per nucleus. Okay, what this curve tells you is that if you were to fuse together elements like hydrogen or helium, and when you fuse together elements, you get a heavier element, so you're moving from left to right as you fuse them together. This tells you how much mass you lose. And remember, mass equals energy by E equals mc squared. So this tells you how much energy you can get out by losing mass by fusing light elements into heavy elements. That's going from here up to here. Or it tells you if you start out with a heavy element and break it apart, like uranium, if you break it apart, how much mass you lose, and therefore how much energy you can get out. So this one curve here is telling you a tremendous amount. It tells you that you can get a huge amount of energy by fusing together hydrogens into helium. So hydrogen down to helium, you get a huge amount of energy. It tells you also that you still get more energy if you fuse heliums together. If you fuse heliums together, you can keep fusing things together and get more and more energy out until you reach the bottom of this curve, where you reach iron and nickel. And so this tells you actually that stars, and we'll talk more about stars in general later, stars can fuse elements and create elements until you reach iron and nickel, and then they die because you can't fuse and get more energy out anymore. It also tells you if you have heavier elements that instead of fuse, they are fissile, they break apart. It's called fission when they break apart. So heavy elements like uranium can generate energy by breaking apart. Okay? And you see that you get more energy from fusion. That's why everyone is excited about one day creating fusion reactors. You get less energy, but still some energy from fission. And then again, you can have radioactive stuff decay away until you reach iron and nickel, and then you're done. So this is what's exploited by the sun, is fusion of light elements to produce heavier elements. We'll talk about the specific reaction inside the sun, but most of the energy comes from, say, combining in the sun hydrogen of form 2 called deuterium and hydrogen 3 called tritium to form helium plus a neutron. And the idea is you're starting out with things that are lighter, and then they snap together in fusion, and then it's lighter. So you lost mass. And where did that mass go? It went into energy. we know of a number of types of fusion reactions. There's two main types that happen in stars, and I'll go over those. We're hoping to produce fusion in future reactors to produce energy. And we also, since the 1950s or so, have been, unfortunately, making nuclear weapons that use fusion to create bombs, right? Fission is another way of making energy, right? That's the other side of that curve of binding energy, says that you can also start out with a heavy element, and when it breaks apart and you add up all the masses, you have less mass than you started with. So again, that mass energy had to go somewhere. It went into energy. And so this has been used for a long time, since the 1940s, right? We had the nuclear bombs we dropped in World War II. We have nuclear reactors that use fission. Okay, and this is, when we think of radioactivity, this is what we're thinking of, is nuclear fission. And when you have fusion or fission, you produce decay products, right? This is actually why we don't like radioactivity, because it produces rays that come out. Rutherford was the first to characterize these rays and give them names. Okay, and there's 4 types. There's alpha, that's the Greek letter A, alpha, which is a helium nucleus. And it's given the name alpha because it's the least penetrating, meaning if I hold up a piece of paper, it will stop alpha radiation. Okay. Beta is a little bit more penetrating, so it's given the name beta. You can stop it with a little bit of aluminum. Okay, and these are electrons. So you have a lump of uranium, it'll emit alpha particles that are stopped by paper. It'll emit beta, or electrons, that are stopped by foil. It'll also emit gamma, so alpha, beta, gamma. It takes lead, right? So this is like X-rays. Like, this is why when you go to a dentist, they put that lead apron over you to stop gamma rays. And then finally, there's neutrinos. Okay, neutrinos are the most penetrating. They actually are extremely penetrating. It takes light years for them to get stopped in some material. So they go through everything. But this is the energy that's actually released inside the sun, okay, or from radioactive stuff. This is what's being produced, and this stuff is how the energy gets out of the sun, right? Some questions. So here's just so this is the sort of thing I want you to know, right? So like nuclear power plants, right? Current nuclear power plants generate energy by nuclear fission. Fusion we're working on, but currently there's no such thing as nuclear fusion reactors. That would be really exciting if it happened. It'd basically be unlimited energy on Earth. We're working on it. But the sun can sustain nuclear fusion. That's where it gets so much energy. There's 2 main processes here. There is what we call the proton-proton chain, where the sun is fusing together hydrogen or protons into helium. And that's anytime you have a star that's greater than about 4 million degrees on the inside, you do that. Then there's also the carbon, nitrogen, oxygen cycle. It's not very important in our sun, but becomes much more important in larger stars whose inside is greater than about 13 million degrees. So I'll talk a little bit about both of these. In either case, what you're ultimately doing is taking 4 protons, snapping them together, and producing an alpha particle, which is helium. So you take 4 hydrogens, produce a helium, plus all of these rays that constitute the energy that's coming out of the sun. Okay. So think of 4 hydrogen in, 1 helium out, plus energy. Each time we do this for 4 protons to get 1 helium, we produce, this is the units we use, MeV, or million electron volts. So we produce 24 million electron volts. You can actually calculate this yourself by just looking at a periodic table. This is what's so amazing. Because each hydrogen, if you look at a periodic table, it's 1.008 U, or atomic mass units. And there's 4 of them. So you add up all that mass. So 4 times 1.008, and then you compare to what you end up with, which is 1 times the mass of a helium atom, 4.003. And what you see is that you lost some mass. You lost 0.03 atomic mass units. And if you convert that to kilograms and then multiply by the speed of light squared, you get, either in joules or in millions of electron volts, you get what I just told you, the energy produced by each reaction in the sun. Here's how you do it, right? So here's where you get that. Any periodic table, most periodic tables show you. So here's the mass of a hydrogen, here's the mass of helium. So 4 masses of a hydrogen are more than the mass of a helium. Where did that mass go? It went to energy. So the sun is fueled by E equals mc squared, mass turning into energy. Now, it requires a lot of 2 protons. Remember, they want to repel, right? Electromagnetic force causes them to want to repel. So in order to get them to snap together, you have to have high temperatures so that they're hitting towards each other really hard. Remember, high temperature means that things are bumping up against each other really hard. That's why you need about 4 million degrees before you start snapping together protons to form helium. Okay. So you need very, very high energy, temperature, before you can start fusion. And then you can begin the proton-proton cycle. So this is the main source of energy in the sun. First, you snap together 2 hydrogens to form hydrogen 2. Then you snap 1 hydrogen onto 2 hydrogens to form helium-3. Then you snap 2 helium-3s together to form 1 helium-4, which is normal helium, plus 2 more hydrogens, which then go back and continue the cycle. And so the net effect is 4 hydrogens become 1 helium, plus these rays that are the energy output. There's one other cycle that's really important called the CNO, or carbon, nitrogen, oxygen cycle, that essentially does the same thing, but through a different pathway. Now, there's a little bit of carbon, nitrogen, and oxygen floating around in the sun. And what can happen is that hydrogen will snap onto a carbon to produce nitrogen-13. That nitrogen then decays to carbon-13. So now you have a carbon-13 floating around that snaps onto hydrogen and forms nitrogen-14. Then nitrogen snaps onto a 3rd hydrogen to form oxygen-15, which then decays to nitrogen-15. And then finally, a 4th hydrogen snaps onto nitrogen-15 to form carbon-12 plus helium. And notice that that means that you're left again with carbon-12 that can start the reaction over again, plus helium. Okay, and so this reaction on net took 4 hydrogens to produce 1 helium plus energy, the same as the other reaction. The difference is that this one, this reaction tends to happen more in stars that are hotter. So you need to be a bit hotter for this reaction to happen. So this only generates about 1 or 2% of the energy in our own sun. Okay, so just as a reminder though, at the end of the day, whichever cycle you use, what's happening is the sun is converting 4 hydrogens or 4 protons into helium plus energy. So the sun slowly is losing hydrogen and building up helium. Note that in all of these processes, in order to produce these neutrinos, I just wanted to mention the process where those neutrinos are produced is called beta decay. That's where you have a proton that gets converted into a neutron plus electrons and neutrinos. Okay. This will come up again in a second just because neutrinos happen to be one of the important ways of studying the sun because they escape the sun so easily. One thing to understand, right, just if you step back, this is in the center, the core of the sun, right? What is nuclear fusion doing? It converts hydrogen into helium plus energy in the form of gamma rays and neutrinos. Okay. Now, you might wonder, right, how does the sun maintain like a steady size, doesn't blow itself apart, it doesn't under gravity shrink to zero? This is a concept of the solar thermostat, okay? It actually makes a lot of sense. So imagine that the sun's temperature in the core dropped. So imagine that the temperature went down. What would happen? Well, if the temperature went down, the fusion would slow down. The pressure in the core would go down. And if the pressure goes down, it can't support itself against gravity, so it starts to contract. But remember, what happens if something contracts under gravity? It heats back up again. So that will then heat it up again, which increases the fusion rate, which increases the pressure. And so you've restored equilibrium. Conversely, you can imagine the opposite. What if the core got too hot? Well, then the fusion rate would start accelerating. But that'll increase the pressure on the core, which will balloon the star outward until it cools down, restoring equilibrium. Okay, so no matter what happens, if the core gets too cold or too hot, it has a natural thermostat that automatically regulates the star so that it stays at a constant temperature and size. Now, eventually, as we'll talk about later, the star will begin to run out of hydrogen, and that will change the characteristics of the core and will change the size and output of the sun. But like right now, for example, there is a plot showing over 10 billion years, the temperature of our sun, the size and amount of light output by our sun. Over the next million years, it's going to stay constant because the solar thermostat keeps the sun regulated. But yeah, eventually we'll run out of hydrogen. We'll start building up helium, and actually that will start to break the sun's thermostat. And the sun will start to get brighter, it'll start to get larger, and eventually it'll start to get redder, it'll start to get cooler on the surface because it'll balloon out, and its surface will cool off. It'll enter a red giant stage. We'll talk all about that when we talk about the life and death of stars in general. Okay. Any questions so far? I have a sore throat, so I'm hoping to get through this soon and get you out to spring break. Okay, so I do want to say, how do we know about what's inside the sun, right? How do we probe the inside of the sun? It's actually interesting, in the 1920s even, no one knew what the sun was made of. No one knew what had created the energy in the sun. It's actually relatively recently where we know all this. Here's an Onion. I like to include Onion articles sometimes. NASA baffled by failure of straw shuttle. This is a pretty funny one if you read it. They tried to go up with a straw shuttle on a mission to the sun to scoop up sun rocks. Anyways, the point is that we can't land a spacecraft on the sun and scoop up sun rocks because it's so hot, right? So how do we learn about the inside of the sun? So 3 things, okay? We have mathematical models that can predict the luminosity of the sun, right? We know about fusion, so we can predict the luminosity of the sun. We can predict vibrations, so this is called helioseismology. We can predict vibrations on the surface of the sun. And we can also predict the neutrinos coming from the sun. So I told you that these neutrinos escape the sun very easily. And so if we look through neutrino telescopes, we can learn a tremendous amount of the sun from that. And so we predict these 3 things, and then we observe them. So these are the 3 ways we learn about the inside of the sun. So let's go through them. Okay, let me ask you a poll question first. So I just mentioned 3 ways that we can probe the interior of the sun. Tell me which is not a way of probing the interior of the sun. Give me 10 more seconds. Okay. Okay, I'm glad most people got that right. We can't take X-ray images of the interior of the sun. In fact, we can't see the interior of the sun. So we can't see below the surface of the sun. So we have to. Well, the one caveat to that is we can use neutrinos. So I'll talk about neutrinos because neutrinos just escape the core of the sun. Okay, but in terms of visible light, ultraviolet X-rays, and then these three other things are the things I just mentioned. Building mathematical models, detecting neutrinos, measuring the solar vibrations. Let's first talk about vibrations. So this is called helioseismology. And it's a study of how the sun vibrates. And we can make models of how the sun vibrates and compare it to observing. And the way we observe is the same method we use to tell how fast stars are moving, the Doppler shift. Remember, something that's moving toward you is shifted blue, something that's moving away from you is shifted red. This is all shown here just in terms of what's brighter is moving towards you and what's darker is moving away. And this is called, therefore, a Dopplergram. It's showing the movement of the surface of the sun. And the first thing we see if we just take a picture of this is that one side of the sun is brighter than the other. And that's just because the sun is rotating. So one side is rotating towards us, one is rotating away from us. So if we take a single snapshot after we've subtracted that rotation component out, we get something that looks like this. And these light and dark spots are the little vibrations, things that are vibrating in and out on the surface of the sun. And then if we average over a whole bunch of those vibrations, we get something that looks like this. And what's interesting here is we're actually seeing, so remember we talked about the granules on the surface of the sun? Here we're seeing basically those granules. We're not seeing much here, but we're seeing a lot on the edges because we're seeing as that convective flow rises up from those granules, it spreads out. So actually we can see on the sides, it's spreading out towards us and away from us. And this gives us a tremendous amount of insight about even what's happening on the inside of the sun, because that's what's generating that convection that causes that rising up and falling and spreading out on the surface of the sun. Probably the most important thing for understanding the interior of the sun and confirming that our theories about what produces energy in the sun is correct are solar neutrinos. Okay? So as a reminder, these are the types of radiation produced inside the sun. Alpha, beta, gamma radiation. Gamma is just light. But neutrinos are a type of particle that can pass through light years of lead without ever interacting. And as a result, these things, once they're produced, escape the sun. And some of them hit the earth, and we build these enormous underground detectors and caverns that can detect some of these neutrinos. Because luckily there's so many produced that even though very few of them interact, we can detect a few of them. And this leads us to see exactly what's going on in the inside of the sun. So by the way, here's a picture showing all of the particles we know, called the standard model particles. There are up and down quarks. These make up protons and neutrons. There's the electron and the electron neutrino. And it turns out there's 3 generations of these, called the second and third generation. So there's electron and electron neutrino, there's muon and muon neutrino, tau and tau neutrino. These are called the force-carrying particles. So photon, W and Z, gluon, the Higgs boson. Now, and here's their masses. So if we look at all of these fundamental particles, there's some really massive ones like the top quark, W and Z boson, Higgs. These are what make up atoms, up and down quark and electrons. That's all the stuff that makes up atoms. And then there's these super light neutrinos. We don't even know exactly what their mass is because they're so light. We just know they're very, very light. That's what these little arrows represent, that they could be anything below that. And so these kind of massless, ghostly particles escape from the sun, and we measure them. And they're produced in 2 main ways in the sun. We have anytime a proton snaps together with a proton, right? So 2 hydrogen atoms snap together, you produce a deuterium, that's hydrogen 2, an electron, and an electron neutrino. So you expect to see one electron neutrino every time 2 hydrogens snap together in the sun. But you also get one whenever you have a little bit of beryllium snaps together with an electron to produce lithium and a neutrino. So those are the 2 main ways. And we've measured the flux of neutrinos at the Earth is about 70 billion per second per square centimeter from the sun. And everything seems to match up with our theory. This is just a reminder that if you were trying to stop neutrinos, if you wanted to build a shield to stop neutrinos, like when you're at a doctor's office with x-rays, you need a light year of lead. That's how hard it is to stop neutrinos. But anyways, I was just talking about, there's all these neutrinos hitting the Earth if we can detect them. They were first detected in the 1970s. Well, this was one of the first big neutrino experiments where they took 100,000 gallons of dry cleaning fluid deep underground in a mine. They do it deep underground because otherwise there's cosmic rays all the time that interfere with your experiment. And they looked for cases where neutrinos interacted with atoms producing a clear signal. And everything made sense except we detected 1/3 of the expected neutrinos. Okay? This earned a Nobel Prize in Physics in 2002. So this was a big deal. Our theory of the sun made sense, except that we only detected 1/3 of the neutrinos we expected. What was one of the big experiments that solved this riddle was called SNO, Sudbury Neutrino Observatory. And this is another deep underground giant detector. Okay. And then around the year 2000, they showed that, yeah, there's 1/3 of the electron neutrinos, but in fact, the other 2/3 are muon and tau neutrinos. And what we learned since then, oh, here's one of these detectors. So it's this enormous tank of water, and what they're doing, they're servicing it in a little raft. And these are all the really sensitive light detectors that fill this giant cavern. When it's operating, it's filled with water and it's dark. And these are all the little cameras basically that are trying to detect neutrinos. But so what solved this riddle is what's called neutrino oscillation. Okay, this solved both that solar neutrino problem, but also solved a similar problem for neutrinos produced in our atmosphere. And this, like puzzle pieces, totally solved the problem. Now we totally understand exactly what's happening in the sun, as long as we account for the fact that neutrinos can change from electron to muon to tau type. So the solution to the solar neutrino problem was that whenever electron neutrinos are created in the sun's core, on their way to Earth, they could change into a muon or a tau neutrino. And as long as we try to detect those, then we can work out exactly how many neutrinos were produced in the sun, and it matches exactly what we expect. Okay, I'm losing my voice, so it's good that I think this is what I wanted to cover for the sun. Are there any questions? All right, again, no homework, but this over spring break, but check the calendar. There is a quiz, so check D2L and have a good spring break. Stay safe, everyone.
Thank you, Professor.
Thank you. What you want, boy?